Hello, and welcome back to High Peak Education for another lecture video. This will be the last in a series of lecture videos on magnetism. We will say a few more things about electric current as it relates to magnetism. We will also briefly discuss solenoids, electromagnets, also Ampere's law, which is an easier way, or at least a more thorough mathematical way, to define how a magnetic field circulation is related to electric current. And then for that matter, we will also discuss Gauss's law once again, but Gauss's law for magnetism, and write down a very nice equation. So thus we will have 3 of Maxwell's equations by the end of this lecture. Now the one equation, Ampere's law, won't be in its absolute full form, but that will be discussed later in the course. Let's have a look at the magnetic force between 2 conducting wires. Let's suppose instead of a single wire producing a magnetic field, or a magnetic force on a wire due to a magnetic field, suppose we have 2 wires interacting. And let's think about what the magnetic forces between those wires will be. Suppose you have 2 wires moving upward, if depicted 3-dimensionally, that are separated by a distance r. And if you were to look at a top-down view, both the wires would be coming out of the page toward you. Again, separated by a distance r. Let's let the magnetic field due to wire 1 be B1. And remember, these are concentric circles around that wire. That is, we're using right-hand rule 3. And that magnetic field of wire 1 at the location of wire 2 is the external magnetic field of wire 1 impinging on wire 2. So we have a current, which is out of the page, and then we have a magnetic field, and the force should be towards wire 1. Now if you work out the same sort of thing for wire 2's influence on wire 1, then you actually also find that the force is towards wire 2. That's actually a statement of Newton's third law. So, right-hand rule 3 describes the magnetic field direction near wire 2 coming from wire 1. Thus, there is a force on wire 2 from the B field of wire 1. The magnetic force per unit length of the wire is found using the magnetic field expression and the magnetic force on the wire. So we get the following expression. Magnetic force per unit length, so this is newtons per meter, is equal to mu naught I1 I2 over 2 pi A. Now A is the distance between these wires. Sorry for not coordinating this, but this R is the same thing as A. It's the distance between these 2 wires. And I1 and I2 are the currents on wire 1 and wire 2 respectively. Mu naught is the permeability of free space, 2 pi, and then L is the length of the wire. Now by the way, sometimes we don't necessarily know the whole length of the wire, but we just calculate force per unit length of wire. Okay? So, notice that previously here, the forces attracted the 2 wires together when the wires had current running in the same direction. That's the so-called pinching effect. But when wires are moving in opposite directions, they move apart. And that's because when I say moving in opposite directions, that is, their currents are moving in opposite directions. So if you work out the geometry and the vector directions, the forces will be away from one another when the currents are in opposite directions. Notice that if you have 2 wires that have forces toward one another, that's because they're pinching. And again, the magnetic field of wire 1 at the location of wire 2 here looks like it's into the page, but the magnetic field of wire 2 on wire 1 here looks like it's out of the page. Given if you do right-hand rule 1b, I cross B is the direction of the magnetic force, and then I cross B is the direction of the magnetic force. So it should be towards one another. And again, it's just the opposite when the wires repel. So we should have into the page and into the page magnetic fields, and the currents being in opposite directions. So the forces are away from one another. An example you might think of is, let's say you have jumper cables, and those jumper cables are near one another. And there's a huge amount of current that runs for a short time when you start another car, maybe 150 amperes. So that the fact that the currents are moving in opposite directions, there's a strong effect of pulling the wires apart. Okay? So that's generally what you would like. You wouldn't like those wires to pinch together. Okay? So if you have the magnetic force between two conducting wires and their loops which have current running in the same direction, let's say both clockwise as viewed from the right, there's an attractive force between those loops. But if you have current moving in opposite directions, there's a repulsive force between those loops. And by the way, this has been observed in metal devices to cause significant pinching or repulsion depending upon if the current is moving one direction or the other direction on the outside of a conducting hollow surface. I will show this example problem in a later video. Now let us discuss Ampere's law, named after the French physicist André-Marie Ampère. Let's first define it. Let us choose an integration path to evaluate some line integral of a magnetic field around a closed loop near a long wire. Suppose this is a closed loop. And suppose this is the direction of our wire, and this has current I going upward. So we note that if we point our thumb in the direction of the current, the magnetic field line should circulate around. Suppose ds is a tangent vector tangent to that magnetic field line path. Suppose we wanted to know what the line integral was of B dot ds. That is, how much is the magnetic field B vector parallel to each of these ds's, and then add them all up. That is, take a line integral around a closed circuit, that is, around a closed loop. I don't mean electric circuit, I mean a closed path. Now, around a straight current carrying wire, that path will exactly be a circle, but in general, some path. What Ampere tells us is that if you take that circulation, if you will, line integral, and figure out how much circulation you have of the magnetic field, that is related to how much current pokes through, that is, penetrates this closed surface. So it's mu naught times I, and I is the I penetrated. Now, by the way, a lot of books call this I enclosed, making a similar analogy to Gauss's law. Gauss's law said you had to have an enclosed charge to have an enclosed electric flux. Here we're saying we have to have, it's like the word enclosed, but I think better said, we have to have an electric current that penetrates through this loop, through the area of this loop. And this loop forms a closed circuit, but that closed circuit has a certain area associated with it. As much electric current pokes through that circuit, that times mu naught will be the total B dot ds closed loop line integral. So this general result is called Ampere's law, which is for a steady current distribution. In other words, one that doesn't change in time. As long as this electric current is constant with time, the closed loop line integral of B dot ds will equal mu naught times that penetrating current. This closed integral path is sometimes called an Amperian loop. Now think about how profound this is. If in Gauss's law we had a closed surface, the surface has a surface area, but it encloses a volume. What we're going to have now instead is we're going to have, instead of a closed surface, we're going to have a closed loop. And the loop length has length of an arc length, but then what's inside of there is an area. Okay? So that's the dimensions. So it's sort of the magnetism and current analogy to Gauss's law, except that it's a closed loop, and then it's not enclosed charge, it's really enclosed, but really penetrating current, because current moves through that area. So the I penetrated is the total current penetrating through the area enclosed by the loop. Note that this B dot ds, dot product, is going to have magnitude B times ds. ds is an infinitesimal tangent length segment, times the cosine of the angle between the magnetic field vector and the unit tangent vector. This law describes the amount of magnetic fields that circulate by continuous current configurations. Okay, so it turns out that even though this looks like a difficult equation, just like Gauss's law looked like a difficult equation, certain geometries are greatly simplified and certain problems are made much easier by using Ampere's law. So here's a little bit more about the geometry. Suppose this is an Amperian loop, okay? And suppose this is the direction of the magnetic field, and suppose this is the direction of ds. Let's let this be the angle theta, and again, on the previous slide I called it the angle phi. But anyway, it's the smallest angle between the unit tangent vector and the magnetic field vector. Let's let the direction of the Amperian loop be the direction of the line integral. So we're going to integrate that dot product of the magnetic field and the tangent to the path around the whole path. Now we want to often strive for symmetry, just as we did with Gauss's law. For this, at least for the sake of this class, we'll often strive for symmetry for ease in mathematical calculation. So again, this is the magnetic field analog of Gauss's law. There is only a net circulation of magnetic field lines if there is a net enclosed current inside the Amperian loop. So the idea is that Gauss's law said you had to have an enclosed charge to have a net flux, and thus to have something you know. If you know something on the boundary, in other words the flux, you know something about what's going on inside. Ampere's law says if you know something about the boundary circulation of magnetic field, you know something about what's going on the inside. Now, like Gauss's law, we choose the geometry of the integration. So we don't let the geometry dictate it to us. We choose the Amperian loop. Now, by the way, notice that in this particular case, I1 and I2, those two currents, would contribute to Ampere's law because those are enclosed. They're penetrating, that is, through this Amperian loop. I3 would not contribute. So keep that in mind. Now, let me also say a few more words about line integrals. I'm going to assume that not everyone that's watching this video is extremely familiar with line integrals. So here's the finite interpretation of a line integral. Suppose you have a curved line from initial to final, from subscript I to subscript F. You could imagine dividing that line into many small segments and call each segment delta S. And the sum of all those little tiny delta S's, those little arc lengths, give the total curved length L of the line. So figure A shows a curved line, and the length can be found by adding up all the delta S's. K here is an index, and then if it becomes infinitesimally small delta S's, those delta S's become ds using calculus, and you integrate from some initial to some final point. Well, how about if you're performing a line integral and there's also a magnetic field? So if there's a magnetic field, like so, notice that you might be interested in what's the magnetic field at some point of interest. So there's a little delta S. Remember, you could take that delta S and shrink it to a ds vector. And you want to know what is the angle between delta S and this magnetic field B. So the figure up here shows a curved line which passes through magnetic field B vector. We can find the line integral of B vector from initial to final as measured along this line in the direction by taking each segment. K here is a counter, and we take dot products of each of these segments and add them up. Now, if it's continuous, that is, if we allow using calculus the line segment to shrink down to infinitesimally small, we have B vector dot ds vector integrated from initial to final. Okay, I will perform this example problem to show what the magnetic field is on the interior and the exterior of a straight current carrying wire using Ampere's law. This will be much easier to calculate compared to using the Biot-Savart law. Now, another important application of Ampere's law is a solenoid. And a solenoid is multiple current loops. So if you have multiple current loops very tightly wound in sort of a helix fashion, it's a very long wire wound into that sort of shape. And you should take the magnetic field vector sum of all the loops. So we need to know the number of loops here. Now, by the way, we assume these solenoids don't have a very large radius and they're very long for the sake of this class. That's an ideal solenoid. And these produce a nearly, not perfectly, but a nearly uniform magnetic field inside and a weak magnetic field outside them. And by the way, the uniform magnetic field is roughly all the same direction and roughly all the same magnitude on the interior of this solenoid. So an ideal solenoid, I already alluded to this, is one where the length is much larger than the radius. It produces a uniform field inside and a nearly zero field outside. The magnetic field of an ideal solenoid is given by this equation. So capital B subscript S of a solenoid is mu naught times lowercase n times I. Now, lowercase n here is not an integer, nor is it number of moles or some counting number. It's the number of turns per unit length. That is to say, it's the integer number of turns divided by L. And L is the length of the solenoid. So it's just going to be a counting number per meter. And then notice that I is the electric current, and then there is our permeability of free space again. Again, that's 4 pi times 10 to the minus 7th Tesla meters per ampere. What are some important solenoid applications? Okay, well, one of them is a nail electromagnet. Notice that if you have some batteries here and you hook up this magnet, you have a very tightly wound coil here, and thus you're producing a very strong magnet. You can not just pick up, say, one paper clip, you can pick up many paper clips. So the electric current running in that coil is going to produce a strong magnetic field. Another example would be a junkyard electromagnet. Notice there's a very tightly wound coil with a lot of current running through this machine. We can pick up enormous pieces of metal as long as they are ferromagnetic, that you can induce some sort of magnetic field inside them. And a medical application would be magnetic resonance imaging, that is MRI. So we can image inside of a person. This is a very expensive machine. If the person is inside and there's this very large coil and a lot of current running through there, and we can find out some interesting medical things about the patient. The last thing I want to say in this lecture is another one of Maxwell's equations, namely what I'm going to call Gauss's law for magnetism. Now, by the way, I should have mentioned earlier, Ampere's law is also known as one of Maxwell's equations for electromagnetism. But we're actually going to modify and finish Ampere's law in a later lecture in terms of what if the current is not steady, or for that matter, what if there's current that's not necessarily through a conductor. So the question is, what is the net flux of magnetic field lines over a closed surface? And I do not have to tell you even the type of magnet. So suppose we have a bar magnet here. Magnetic field lines move out of north into south, and in the magnet itself, in the dipole, they go from south towards north. Notice if you take this surface 1 or this surface 2, it doesn't even really matter the surface. Now I'm talking about a three-dimensional surface that has surface area and that it allows you to have magnetic field lines moving into the surface and out of the surface. Notice the same number of magnetic field lines that exit that surface also at some point later enter the surface again. Notice that's the same with surface 2. Every magnetic field line that enters exits. So the net flux over that surface is actually going to be 0. Remember Gauss's law? If you take the closed surface area integral of electric field vector dot dA, you get the enclosed charge. But if you do the same thing for B dot dA, that is magnetic field dotted with some differential area, you get 0. Another way to say this is that del dot B vector, for those of you that have had some vector calculus, this is the gradient vector dot product with the magnetic field equals 0. That is, the magnetic field is what we call divergence free. In other words, there's no net convergence or divergence of the magnetic field. Magnetic field lines have no beginning and no end. They form closed loops. That is to say, there are no magnetic monopoles. So this means that all the magnetic field lines entering equals the magnetic field lines exiting a volume. And so there are no magnetic monopoles. And this is actually the third of Maxwell's equations that we'll leverage, because this tells us about the nature of magnetic fields. Ladies and gentlemen, thank you very much for your time and for your attention and for watching High Peak Education. Please smash that like button if you enjoy this content. Please share it amongst your social network. And I look forward to seeing you in the next video. Please feel free to comment, and thank you, and see you next time.